organisers. Well, that's good to know. Thanks very much for the organisers for inviting me here today. It's great to be in London, and it's great to celebrate the wonderful life of Lord Kelvin. And the second thing I have to do, in fairness, is kind of apologise for the title. When I read it off the page, I realised it's a wee bit too terse, isn't it? A wee bit too mysterious. That's because, ironically, it was written in some haste. It comes from this book by David Wilson. David Wilson was taught by Thomson in Glasgow in the 1880s, and he says, he seemed ever in haste, yet his haste seemed without hurry. And this is backed up by a number of other voices. For example, Dr. Redtail, William Thomson's parrot, who would berate Thomson when he arrived late to lunch from the lab with, "Light again, Sir William, light again." That might have been his accent, I don't know. And then there's Sylvanus P. Thomson, his official biographer. There's going to be a lot of Thomsons in this talk. And he said time was his enemy, with whom he seemed to wage continual warfare. And then back to David Wilson again. Another thing familiar was the quick limp of his walk, which made more than one who knew him well associate mental rapidity with lameness. What differentiated him was an enthusiasm for knowledge that blazed within him like a volcanic fire. And he got that limp from a curling accident on the ice in 1860. And then, of course, we're celebrating 200 years. 100 years ago, here in London, there was the centenary celebration. Here's the book of the gig. And the main speaker at that wasn't any of us. It was Sir J.J. Thomson of electron fame. And he says, to be interested in something was, with Lord Kelvin, synonymous with discovering something new about it. And those paint a picture of Kelvin being a brilliant, busy, inquisitive, creative man. And he was all of those things. He was all of those things. He was a hugely influential figure in 19th century science. And over the next 30 minutes, I'm really just going to be painting with a very broad brush on some aspects of his life. So to begin at the beginning, and the beginning is in Belfast in 1824. Thomson was the middle of 7 children. And when he was born, his father, Dr. James Thomson, was Professor of Mathematics at the Belfast Academical Institution, which at that stage was a school and a college combined. And the aim of that college was to save not only the young boys of the province of Ulster the trouble of having to go across the Irish Sea to get an education in Scotland. One of the Thomson's childhood friends says of James Sr., he was a stern disciplinarian and did not relax his discipline when he applied it to his children. And yet the aim of his life was their advancement. James Sr. was hardworking and ambitious. He would get up at 4 o'clock in the morning to write books on arithmetic and geography and calculus, and then walk across the road to take his morning classes. And he was hugely ambitious for his children and their education. And that comes across in William's life and in his older brother, James Jr.'s life. James Thomson Jr. ended up being a very significant engineer in his own right, both at the Queen's College Belfast and then at the University of Glasgow in later life. In 1830, William's mother dies. In 1832, the family moved lock, stock and barrel to Glasgow, where their father has been appointed 6th Professor of Mathematics at the university. James and William are attending his classes from the get-go, but they don't enroll formally to the 1834 session. When James is 12, William is 10. Now, that's young, but it's not quite as young as it sounds. You could be in your mid-teens and enrolling at a Scottish university in the early 19th century. And William was at very least a precocious boy. He came across Fourier in his natural philosophy lectures at Glasgow, and he says, on the 1st of May, 1840, I took Fourier out of the university library, and in a fortnight, I had mastered it, gone right through it. William Thomson is 15 at the time, and he's reading the analytic theory of heat, the show off, in the original French. Okay. And this work led to his first paper the next year on Fourier. As was mentioned, he was 16 years old. It was published pseudonymously under PQR. And by the time he was 20, he had published a dozen papers, 10 of them under the pseudonym PQR. And as we're going to see, Fourier bobs up all over the place, well, in multiple places in Thomson's work during his career. Again, I'm going to channel J.J. Thomson a number of times during this talk from his centenary address. I have heard him say that whenever he had done anything with which he felt particularly pleased, Fourier's theorem was always at the bottom of it. William finishes his education at Glasgow, but he doesn't take the degree. There was some unfounded worries that this might prejudice his case for going to enroll at Cambridge. And therefore, around this time, in letters to his brother, he would sometimes sign himself off, William Thomson, Bachelor of Arts to all intents and purposes. He enrolls at St. Peter's, or Peter House in Cambridge in 1841, aged 17. And he's working hard. He writes a letter to his dad. I have been going on reading steadily about 8 hours a day and getting up perfectly regularly, a little before 6 o'clock. That was the truth. It was the truth. Not quite the whole truth. If you read his diaries, you'll see that he's also got a very full social life. He's rowing, and he's rowing very well. And he's a founder member of the Cambridge University Music Society as well. He's enrolled under the private coach, William Hopkins. The senior wrangler maker was his other name, and that was a well-earned name. By 1849, William Hopkins had 200 wranglers to his name, and 40 of those wranglers were in the top 3 positions on the lists. So he was good at his job, and if he wanted to do well, he was one of the guys you were going to enroll under. The final start, 1st of January, 1845, 6 days, 12 papers back to back, morning and afternoon. And when the results are read out, to universal surprise, William Thomson is not senior wrangler. He's second. A guy called Stephen Parkinson is senior wrangler. And one of the explanations for this is bluntly, Parkinson could write faster than Thomson. Right? I mean, there was lots of book work in the Tripos papers. You had to be able to write fast to get through all the work. And one of the examiners said if he hadn't have been in the room and seen Parkinson write, he wouldn't have believed anybody could write that flipping fast in 2.5 or 3 hours. When it came later in the month to the Smith's Prize papers, which were more problem-based, Thomson easily comes top of the list. And after Cambridge, he goes, missed the slide. Not everybody was all that content about the fact that William had only come second in the lists, and Agnes, for example. I am most desperately disappointed. I am not consoled to learn that so-and-so and so-and-so stood second. I expected him to stand first. And the only thing that reconciles me is that we all know that this mortification. Ants aren't gentlemen, as P.G. Woodhouse says. Anyway, so after Cambridge, where does he go? He goes to France for a few months, and he meets the great and the good. He meets Stern, he meets Louisville, he meets Bayeux, he meets Cauchy. He attends lectures in physics and chemistry at the Sorbonne. He meets, importantly, Regnault, College de France, and spends weeks in his laboratory getting experimental experience. this wasn't a post-graduation jolly. This was strategic. Because from 1839, William Mickleham, who was the professor of natural philosophy at the University of Glasgow, had been ill. And from 1842, when William Thomson is 18, his father is realizing that William could be in the running for the job. But he needs to get some experience. So he sends him to France after graduation to get experimental experience. He tells him when he's at Cambridge, make sure you attend the practical astronomy classes and the classes in natural philosophy as well. And he does. When he comes back from Paris, June, he's elected a fellow of St. Peter's College. That's pretty much automatic for a high wrangler at the time, and not a surprise. Now, rather conveniently, though one can only assume completely unintentionally, Professor Mickleham pops his clogs on the 6th of May, 1846. And James Sr. is immediately writing to his son. The enclosed notice of Mickleham's death must put you into active and energetic motion without delay, he writes to William. And William acts. He's writing from St. Peter's College, Cambridge, at the end of May, signed off William Thomson, Fellow and Mathematical Lecturer of St. Peter's College, to announce to the electors at Glasgow that he wants to stand as a candidate for the chair. James Sr. is a bit nervous because there are other people who could be applying for this job. He's also a bit nervous because there could be potential opposition from within the professoriate at Glasgow. Another Thomson on the faculty list wouldn't necessarily have gone down all that well. However, despite all his worries, on the 11th of September, 1846, William Thomson is unanimously elected to the chair of natural philosophy at the University of Glasgow, and he stays in that post for 53 years until his retirement in 1899. And he's tempted, people try to tempt him elsewhere, but he doesn't go. Now, Professor of Natural Philosophy. Such a one as a natural philosopher, says Touchstone. And As You Like It, brilliant play, go and watch it. Also a prize for somebody who can link that to another member, another president of the LMS. I'll give you a cup of coffee. Anyway, so Thomson, as has been mentioned, was 18th president of the LMS between 1898 and 1900. Now, how am I going to break this to you? London Mathematical Society. Your 18th president wasn't a mathematician. Sorry. He was a natural philosopher. First, he was an engineer. Second, and though, yes, of course, he was a brilliant mathematician, he was always using that mathematics in service to the first two. Says Sylvanus P. Thomson, he scorned all formulas, however neat, if they merely served as mathematical exercises or gained their apparent precision from the adoption of unwarranted assumptions. Or at one stage in a lecture from Glasgow, Thomson writes dx by dt up on the board and asks the students, what does that mean? Some of the students start to give him an answer in terms of a limit. That's what Todhunter would say, says Thomson. Todhunter was a very successful textbook writer in the 19th century. Does no one know that the x by dt means velocity? Says Thomson. For Thomson, a derivative's primary definition was physical. And finally, again, sorry folks, Kelly was your third president. Oh, that the Cayleys would devote what skill they have to such things, i.e. applications, instead of the pieces of algebra, which possibly impress 4 people in the world. It really is too bad that they don't take their part in the advancement of the world, says Thomson to Helmholtz in 1864. And if you browse through the 6 volumes and 661 papers of William Thomson, you'll find a heavy weighting towards physics and application. I mean, you just need to leaf through them to see that. Right, so, sorry about that. Move on to 1847. 1847 at the British Association in Oxford, William Thomson hears this man, James Prescott Joule, give a talk about the mechanical equivalent of heat. Joule is claiming that he can quantitatively link the amount of mechanical work done to the increase in temperature of water. Thomson writes to his father, well, Joule is, I am sure, wrong in many of his ideas, but he seems to have discovered some facts of extreme importance. And this sent Thomson down a path of what he termed thermodynamics. And he was a significant player in this area, showing among many other things, or finding out among many other things, that Joule certainly was not wrong in his assertions. However, you'll note if you run down the schedule for today, I think there's at least 3 other talks on thermodynamic aspects of Thomson's work. So I'm just going to skip it. Okay. Even though it's a very significant bit of science and it's a very significant part of Lord Kelvin's work, I'm just going to look at it and how it hooks in to one very significant book. Now, in 1860, William Thomson finds himself with a new opposite number at the University of Edinburgh. Peter Guthrie Tait had been appointed as Professor of Natural Philosophy. Tait was a Scot, in fact, he was from Edinburgh, but he had just come from Queen's College, Belfast, to take up the post. And I love this graduation portrait of Tait. He's looking at you, out at you saying, yes, quite frankly, I am a lot cleverer than you. So anyway, it doesn't take long before the 2 of them are thinking of writing a book together that they'll be able to use in their respective natural philosophy classes in Glasgow and Edinburgh.
Does he not have the look of a first wrangler?
He does. He has, yes, he has a look of a senior wrangler. But I think he also claimed at one point, oh, I could teach a coal scuttle to become senior wrangler. He says something like that at one point. There were very different personalities. Anyway, never mind. So it all starts well. I fancy that we might easily give in 3 moderate volumes a far more complete course of physics, experimental and mathematical than exists, to my knowledge, in either French or German. As to English, there are none. Tait Thomson, December 1861. And then it all goes sour. What in the name of goodness are you doing with the proof sheets? Send proofs back the 2nd day after receipt at the latest. Tait Thomson, March 1863. Send me my manuscripts and then go and see Macmillan and account to him for deficits and extensions, etc., and promise him on your part, and then you need have no fears about adding mine, that volume 1 will be ready in the end of July. Tait to Thomson, May 1864. And now, in fairness to Thomson, it's the 1860s. He's working on the Atlantic Telegraph cable at the time. Thomson's a very busy man, but it may well explain why in later life Tait was completely bald. Well, partially bald. Now, if it wasn't for Tait, this book would never have been published, arguably. Tait would send ideas to Thomson. Thomson just wouldn't reply. Tait would write his sections. Thomson wouldn't get around to his for months. Thomson would get hold of the proofs, and then interpolate wildly at the proof stage so that for example, something like section 3.8 would become section 3.8, subsection A to subsection F. And that last quote is wildly optimistic. The book wasn't published until 1867, and the book is this: the Treatise on Natural Philosophy, commonly known as Thomson and Tate, or sometimes just known as T and T. And how this hooks into thermodynamics is up front in the preface. One object which we have constantly kept in view is the grand principle of conservation of energy. According to modern experimental results, especially those of Joule, energy is as real and as indestructible as matter. Not something, of course, we take for granted when we're teaching physics now. It wasn't in the middle of the 19th century. And you'll notice giving lots of copy there to a good Brit, Joule. That was controversial at the time. Wouldn't be surprised if that was written by Tate. Tate could quite bluntly be xenophobic when it suited him. Ewan Rhys-Morris, historian of 19th century physics, writes, William Thomson and Peter Guthrie Tate's Treatise on Natural Philosophy of 1867 was a quite self-conscious effort to replace Newton's Principia as the foundational text of a new kind of natural philosophy. But actually the project was never finished. A second edition came out in 1879, which was enlarged, but it still didn't contain the big building blocks of natural philosophy like hydrodynamics or optics or electricity or magnetism. It remained a book on kinematics and dynamics. It was, however, an important and influential book, as was noted by one of its early readers. Let's go back to J.J. Thomson once again. It was quite different from other textbooks. In most of the Cambridge textbooks and in the mathematical tripos at this time, this is the 1870s, the discussion of a problem usually ceased when an equation connecting a number of symbols had been found. In Thomson and Tate, all this was changed. The equations were squeezed and squeezed until all the dynamics and physics they contained had been extracted. There was a kind of fascination of glamour about the book, as indeed there was about many things connected with Lord Kelvin, which kept us working at it in spite of all its difficulties. For, with all its merits, the book is not easy reading. And J.J. Thomson wasn't the only person to think that. As I mentioned, the initial aim of this book was to have something that could be used in Edinburgh and Glasgow in their dreams. So they developed a cut-down version of the book called The Elements of Natural Philosophy, which basically, roughly, had all the heavy maths ripped out of it. This is it, or a later edition of it, the Duffer's Guide. That wasn't called the Duffer's Guide, obviously in the advertising material, but would be today. And J.M. Barrie of Peter Pan fame went to the University of Edinburgh late 70s, early 80s, and took Tate's classes in natural philosophy, and he describes this book as the student's first glimpse of Hades. And in spite of that, or perhaps given Tate's personality because of it, it remained in the syllabus at Edinburgh until Tate retired. Now, on to telegraphy. It is the most wonderful thing. Messages were sent out to Manchester, Edinburgh, etc., and answers were received in a few seconds. Truly marvellous, wrote Queen Victoria in her diary, having just come from the Crystal Palace and the Great Exhibition. And by the end of 1851, there was already a cable going between Dover and Calais. But the big game was to have a transatlantic cable that would link the British Isles with North America. And to that end, the Atlantic Telegraph Company was formed in 1856. William Thomson is on the board of directors from the beginning, but at the beginning he has no technical or scientific role. And it wasn't until a decade later, in 1866, that they finally had a working cable. There were lots of disasters in between. And over that decade, William Thomson became involved in the Atlantic Telegraph project up to his neck. He spent months at sea. He developed on the technical side, for example, a way to pay out the cable so that it wouldn't break. It was 1.7 tons per nautical mile, or mirror galvanometer to detect very small signals, or even insisting that at the factory they made sure the copper was of consistent and high purity to go into the cabling. It was the beginning of Thomson's serious interest in engineering and technology, and it led to over 70 patents, all the way from the aforementioned mirror galvanometer to, believe it or not, a tap that didn't drip, which was being advertised in the Belfast press in the early 1890s. And of course, Thomson was involved on the theory side as well. He writes down this telegraph equation in 1854 in a letter to George Gabriel Stokes. That's where it first sees the light of day, and then it's published later. So that's the capacitance per unit length. That's the resistance per unit length. Oh my goodness, what would that be now? That would just be the one-dimensional heat equation in disguise. How convenient. And so William Thomson was able to show if you have a sharp signal at one end, then it diffused out as it propagated down the cable. And the time to the peak of that diffused signal varied as the square of the length of the cable itself, giving Thomson's law of squares. Of course, that's surprising, because you would expect the signal to propagate proportional to the length of the cable. But some people just thought it was ballywell wrong, including Wildman Whitehouse, the chief electrician to the Atlantic cable. He said, "Nature knows of no such application of that law. I can only regard it as a fiction of the schools, a forced and violent application of a principle of physics." Whitehouse was a thorn in the side of both Thomson and the Atlantic Telegraph Company until basically he was fired for incompetence in 1858. He was an amateur electrician and a professional medic. Now, so and after Whitehouse's leaves 1858, Thomson basically takes over the whole technical side. He's become center stage of the laying of the cable. Autumn 1866, as I said, the bally thing finally works. Thomson basically steps off the boat in Liverpool and is knighted on the spot. He's 42 and he becomes Sir William Thomson. Now, the age of the Earth. So 19th century geologists reckoned that the Earth was, well, what's the phrase? Incomprehensibly vast. That was the phrase that Darwin used in The Origin of Species. Darwin had actually been brave enough to try and put a number on it. He estimated the erosion in the Wheel of Kent had taken 300 million years to occur. Oh, well, it is quite certain that a great mistake has been made, that British popular geology at the present time is in direct opposition to the principles of natural philosophy, says William Thomson in 1868. Now, 1868 wasn't his first foray into this. There's a lot of stuff in the 1860s and 1870s on the age of the Earth from Thomson. Probably the most important paper, most significant paper is his 1862 paper on the secular cooling of the Earth. And he approaches this from three directions. I'm gonna really mention one in any detail. First one was, well, how old is the sun? Right, that's going to give you an upper limit for the whole shooting match. And that comes, and of course, it's 19th century. The heating's got to come from gravitational collapse of meteors. The second one is the slowing of the rotation of the planet due to tidal friction. And then it can work backwards. Think about, well, how fast was it then going when it solidified? And that can account for the flattening of the poles and the bulging of the equator. And the third one is the secular, that just means the slow cooling of the Earth. And he has data for this. There's data from, I think somewhere around Edinburgh at least, in one case of people digging down and the temperatures increasing at about 1 degree Fahrenheit per 50 foot. And he assumes you've got a globe which is solid and cooling. So its maximum temperature has to be at the solidification point of rock. That's about 7,000 degrees Fahrenheit. And of course, he knows that, you know, there are problems here. There are problems with latent heat diffusion or changes, variation in heat conductivity. He comes up with a figure of 98 million years for the age of the Earth. And he says, but because of those sorts of issues, I'm going to put limits on that. It could be anywhere between 20 and 400 million years old, he says. Well, pages of formula will not get a definite result out of loose data, says Thomas Henry Huxley, aka Darwin's bulldog. Thomson responds, I have amply indicated how loose my data are, and I have taken care to make my results looser. I am anxious to be regarded by geologists as one constantly interested in their grand subject and anxious to assist them in their search for truth. And take that last bit at face value, right? Thomson wasn't I don't read his personality at all as curmudgeonly or combative. He just wanted to know the answer. He just flipping well wanted to know, right? He was passionately curious. And that was the result he came up with. Now, and here's the thing I didn't realize until I looked at the papers. So, cooling of a globe, spherically symmetric. So what's he going to do? He's going to solve the spherically symmetric form of the three-dimensional heat equation, isn't he? No, he's not. He's going to solve the one-dimensional heat equation instead. Because he says, look, when you've got something of the size of the Earth, 8,000 miles in diameter, the difference between these two solutions is going to be of, it's not going to be significant until you go more than 1,000 million years into the future. So don't worry about it. I know that this isn't. Thomson was smart, right? But he was also smart enough to know that you don't do more work than you have to. If you can come up with a simple model that works, then you use that one, right? And by the way, he's done that with a telegraphy equation as well. He was ignoring what that was. Right. Where was I? Oh, yes. I was here. So, his work on the transatlantic telegraph, with the transatlantic telegraph company, and his other interest in all things technological had made William Thomson a very wealthy man. 1875, he's built a really rather nice house called Nether Hall, about 24 miles west of Glasgow. 1870, he buys himself a really rather nice 126-ton schooner called Lalla Rook. And remember that quote from Thomson, J.J. Thomson back at the beginning? To be interested in something was, with Lord Kelvin, synonymous with discovering something new about it. So once William Thomson becomes a sailor, he becomes interested in all things nautical and starts to work on relevant problems. And here are just a few of them. He comes up with an improved compass, which was more stable and could cope better with iron-hulled ships that were coming into fashion. He comes up with a depth sounding device, which meant that you could take soundings on the fly when the boat was still moving. Previously, you'd had to stop the belly thing and lower down a piece of rope. He uses piano wire and a pressure gauge to enable you to do it better. Or, and this is to me the coolest thing, he comes up with a completely mechanized way to predict the tides. And he does that using 3 different machines. Here's the first one, your tide gauge. What you do is you drop this down into the water, and it goes up and down, and as it goes up and down, you record that on this drum with a piece of paper on it, which you wind up with clockwork, right? And you take about a week's readings on that. And then you take those readings and you plug them in to your mechanical integrator, which his brother, James Thomson, had helped develop part of. And what you do from that is you integrate out the amplitudes of the various sinusoidal driving frequencies, which are of course coming from the sun and the moon. And then you take those amplitudes and you put them in to this, the tide predictor. And you quite literally crank that handle for 25 minutes and it produces a graph of the tides in the area you're interested in for a full year. Great. Right. Of course, that was big business in the Empire era. If you didn't get your tides right, coming into some of the big ports, you could end up with a ship literally broken in two. And of course, when he's integrating out the amplitudes of these sinusoidal driving terms, what's he doing? Flipping well using Fourier again, right? As Thomson said at the beginning, Fourier just bobs up in all these things that he's really interested in. And a whole, maybe almost a whole volume of his practical, as popular addresses is devoted to nautical stuff, if I remember rightly. Anyway, there's 3 volumes of that as well. So, New Year's Day, 1892, William Thomson is elevated to the peerage. The British Medical Journal said that a peerage had at last been conferred upon a scientific man because he's a scientific man. Well, the British Medical Journal might have liked to believe that, but it probably wasn't really true. If William Thomson hadn't have been involved in the Liberal Unionist cause politically for the last 6 years before this, he probably wouldn't have got a peerage. Here he is with Lady Thomson in 1902, dressed in the appropriate garb for the coronation of Edward VII. Aged 72, he finally retires. Here he is, or 75, sorry. Here he is giving his last lecture in 1899. And then he insists, pretty much immediately, of enrolling, matriculating at the University of Glasgow as a student. Here's his matriculation form. Full name, Kelvin, Birthplace, Belfast, County Antrim. Branch of study, physics and mathematics. Classes for this session, not yet determined. That his replacement was pleased about that.
The youngest and the oldest matriculating student.
Oh, really? Oh, very
10
good.
years old and 75.
Nice fact, yes. And in 1904, he becomes the university chancellor. When the university is publishing its 500th anniversary volume, the guy they have on the page as you open the book is Lord Kelvin. Kelvin dies on the 17th of December 1907, and 6 days later in a foggy London, he is buried in Westminster Abbey, literally beside Isaac Newton. In his lifetime, Thomson had been thought by some to be the second Newton. So where do you put him after he dies? You put him right beside the original version. And here is the Illustrated London News drawing of the burial service. There's the famous monument to Newton in the background there in Westminster Abbey. I've got actually that, and my wife, for strange reasons, won't let me frame it and put it on the wall. She seems to think it's very macabre and depressing. Who knew? Right, so and there's loads of things I haven't talked about with regard to Thomson. Smaller things like the method of electrical images, electrostatics, that's William Thomson. The first solution of the LCR circuit, that's William Thomson. Kelvin's thunderstorm, Google it. It's scientific magic. And then there are bigger things, such as the creation of the first student physics lab in Britain. And that idea is then propagated out to UCL and Oxford and Cambridge and Liverpool after that date. Or his work on the ether and vortex atoms, which was really hot mathematical physics. Or his lifelong friendship and correspondence with George Gabriel Stokes, or the Baltimore lectures at Johns Hopkins University in 1884. But then, just as with Thomson himself, I am ever in haste, and I see time is my enemy. So, naturally, and you're not going to be surprised by this slide, principally because you just saw it flick up on the screen a few minutes ago, but you're not going to be surprised with it. I'm going to finish with this man, John Henry Cardinal Newman, another enormous figure in Victorian life. And it's just disappeared. I can't go on.
You just need to share the screen.
Because I can't remember the quote, that's why I can't go. Talk among yourselves.
This is just to add suspense.
Yes,
To undo the fact that we've briefly seen it.
this is completely deliberate on my part. So. It was there.
Yeah, sorry about this.
No worries, don't worry. Panic, you've just ruined the whole. Sorry, come on. Right, thank you. Okay. So says Sheridan Gilly, there can never be a definitive biography of Newman. Only new Newman biographers. And the same is true of Lord Kelvin. You're not going to go far into the Victorian era without meeting William Thomson and his papers and his patents and his collaborators and his letters and his huge scientific contributions. William Thomson, Baron Kelvin of Largs, bestrode Victorian natural philosophy like a colossus. And when you read the history books, you'll find that he still does. Thanks very much for your time.
So thank you very much for a very exuberant and exhilarating talk. Do we have any questions in the room? And if anyone has questions online, do feel free to put them in the chat. Any questions from the room? Jane?
Thank you, I think you could make a senior wrangler out of a cold. It's a slightly different question, but we always use the terms natural philosopher out of nothing rather than public. So I know in Scotland that was very much the case in the 19th century. But do you see there's any deeper difference, and is there any reason for that?
Oh, that's a good question. My guess would be no. I mean, obviously that the use of terms evolves, but it means the same thing really. Certainly once you've got the once you're getting into the 19th century, that I would say that that's the case. Interesting, when I was applying to universities in 1984, I could still have enrolled on a degree in natural philosophy at the University of Aberdeen, and I nearly applied just to be able to say I could do it, but I didn't.
Yes, yeah, great talk. So one thing you didn't mention, which he was known for, was his green
Oh, the green books, yeah.
Could you mention how he used to retire away from social events?
Yeah, the green notebooks, the famous green notebooks. So, and he was using these for, well, I can't remember when he started using them, but he actually had a little pocket in his coats, so as he could always carry a notebook, and he could be sitting here, pull out something in a cartoon, pull out his notebook, say, the Morgan House, London Mathematical Society, London, date, exact time, and put down a few notes on what I was thinking. And I can't remember how many there are, but there are a lot. I mean, the name of over 100.
What was that, 80 year average, 80 years?
So there's a lot of them. I haven't seen them myself, and I've read some stuff on them. And the person who wrote on them said in some cases they could just be decipherable in terms of what he had done. But it's an example of Thomson as this passionate, interested man. He was having out all flipping well over the place, and he would get out his notebook and write down. Yeah. And say things in detail like, when Blackburn's garden, smoking a pipe at such and such a point in the afternoon, and write a bit of mathematics or physics.
My notebook's not so profound. Did you have a question?
There used to be a refrigerator called a Kelvinator.
Yeah.
Did he invent something in refrigeration?
Yes, he did, but I can't give you the details. There's 3 people talking about thermodynamics. One of them will be able to answer it. But yes, he did, and I think he might have patented it as well. But don't go in there. Yes, he did.
Thank you, so wonderful talk. I just want to make a couple of comments and then a question.
Yeah, sure.
So for the natural philosophers, which I think a very good one, there's a strong tradition of intersecting philosophy and science in the Scottish educational tradition. So for those interested, I recommend the book, The Democratic Intellect, which is a reflection by an Edinburgh philosopher on exactly this tradition. On the refrigeration remark, the Institute of Refrigeration had a broadcast event on Wednesday. Exactly on this. So go online. It was recorded. I think you'll be able to see that. My question relates to David Thomson.
Yeah.
And the intersection with Hamilton.
Yeah.
Because in some sense, the metaphysics, which is part of this natural philosophy question of force, was much on the minds of the 19th century natural philosophers. And in some sense, they got rid of the concept of force, utilizing Lagrangian and Hamiltonian mechanics. So maybe if you could just reflect a little on the impact of that on the development of science and the fight between Tate and Thomson over the use of quaternions.
Yes. Yeah. So, okay. So I'll try to keep it track. Those are very incisive questions. So, when Tate is in Belfast, he's corresponding with Hamilton in Dublin, and he becomes very interested in quaternions. In fact, he just thinks quaternions are the art forms pajamas, and these are very useful things. Thomson definitely does not think Quaternions are anything like the aardvark's pajamas. And I think he says that to take something of the line of, well, you know, if you can find an example of where Quaternions does a better job, then we'll use it in the book. And then he slyly notes, you will note that there are no Quaternions in Thomson and Tate. So, yeah, and again, so Thomson, it comes across as very sort of relaxed. Tate was testy and aggressive and could get into real spats with people, but that didn't blow over into Thomson and Tate. I think they really got on really pretty well. In terms of Lagrangians and Hamiltonians, so certainly they do in the big version, they're doing stuff in terms of Hamiltonians and Lagrangians, if I remember right, and how much of a sea change that is in terms of how much it's picked up, I don't know. I expect it is quite significant, because certainly it's, you know, something like Lagrangian dynamics, it's kind of, again, it's a bit of black magic. You know, suddenly all these sorts of problems with forces are a flipping nightmare. You put it in Lagrangian form and suddenly, ta-da, I come here.
So they could make a couple of comments.
Yes,
So the first thing is.
We're winding down.
Winding down.
We're winding down.
We're winding
It's
down.
time for a break,
Is
so it is,
Come to me after.
yeah. But that means there's 10 minutes for us to comment amongst ourselves. So yeah, if we just thank Mark once again.